Hi, welcome to another 4AC learning video. In this video we want to look at example 4.3a, which is found in the lecture notes, topic 4, AC power. Now a system supplied by a 50 Hz source of 230 volt 0 at a 0 degree, having a complex power of 1000 VA at an angle of 60 degrees. So we want to find the total current flowing into the circuit. We want to find the effective or average power. We want to find the reactive power, and we want to find the power factor of this system. Then we also want to determine the required capacitance to correct the power factor to 0.86, and we also want to calculate the new current source value, whether by putting in extra capacitance, what happened to the current basically. So the circuit can be seen as follows: a black box that has a complex power of 1000 VA at an angle of 60 degrees. We apply 230 volt into the system, and we want to calculate all these parameters. Okay, so let's see how we do this. Alright, we start by looking at the complex power. It's given as 1000 VA. And the angle is 60 degrees. So power factor PF is equals to cosine 60 degrees. That gives me 0.5 lagging, because there's a positive number here. And the current IS, the magnitude of it is just the voltage, or rather the apparent power divided by the voltage 230. So that's equals to 4.348 ampere. So the complex version, IS, is equals to 4.348 ampere, but the angle is 0 minus 60 degrees. The power P is given by S cosine theta, which is 60 degrees. So that is 1000 cosine 60 degrees. That gives me 500 watts. Q is S sine theta, which is 1000 sine of 60 degrees. So that gives me 866 VA reactive. Another method to calculate is use the complex power formula, which is E multiplied by the complex conjugate of I, which is 230 angle 0 multiplied by complex conjugate of I is 348. The negative of that, so it's 0 minus 6 becomes 60. That gives me 1000 at an angle of 60 degrees. Convert that to rectangular version is 500 plus J 866. Compare this against the standard formula P plus JQ. So P is 500 watts, whereas Q is 866 VAR. Okay, so that's for part A. This is part A. Okay, now part B, we have to look at how to improve the power factor. Right, currently the power factor is 0.5. Power factor here is 0.5. Lagging, meaning it's capacitive. So how to improve this power factor? To how much? To 0.86. Okay, so if we were to look at power factor correction, the new power factor that we want is 0.86. Now, when we increase the power factor, the idea is to adjust the reactive power. So the effective or average power remains the same. Okay. And the new power factor now is cosine theta, the new angle is 0.86. So theta, I can do a reverse calculation. Cosine inverse of 0.86, that gives me 30.68 degrees now. Right, and we know the effective power calculated earlier is 500 watts, so that remains. So therefore, if we were to look at the power triangle, now power triangle, we can draw something like that. Huh? The original power triangle P remains the same. The original Q or reactive power is this one, which is 866. This is the original power and the original angle. Sorry, the other way around. The original power is 866 is all the way here. It means from here to here. So this is the original power S, which is 1000. Now what we want to do is we want to change the power factor. The angle, original angle is 60 degrees. We want to reduce the power factor, improve the power factor so that the angle become the new angle, 30.68 degrees. So in other words, we want a new triangle like this. So in order to introduce a new triangle, we must introduce QC such that it reduces this reactive power down. So that's how we get this tangent theta 1 is Q1 over P. Q1, the new Q that we want, over P. Right? You look at this right angle triangle. So new angle tangent theta 1 is equals to Q1 over P. Right? Therefore, the new Q that we need is P times tangent theta 1. So P is 500, tangent theta 1 is 30.68 degrees. And that gives me a value of 296.68 VAR. So the new capacitance so the new reactance that I need to introduce is QC. This one is the original 866 minus what I want to bring it down to. So it's 866 minus this value 296.68. So that will give me 569.32 VAR. Okay, so I need to introduce capacitor into the system of so much capacitance, or so much that will give me so much reactive power. Since the capacitor is connected across the supply, remember we can connect the capacitor here, right? You will see the full voltage that is applied, E square, and XC is the reactance, capacitive reactance that we need to introduce. So reverse this formula, we have E square over QC. So E square is the voltage applied, 230 volt square, divide by QC, that is we want here. So it's 569.32 VAR. Okay, XC. So that gives me 92.92 ohms. But we also know that XC can be calculated as 1 over omega C, or 1 over 2 pi FC. Alright, so that's equals to XC. In other words, equals to this number, 92.92 ohms. Rearrange this formula, we will get XC over, or XC times 2 pi F equals to 92.92 times 2 pi times 50 Hertz. So that gives me a total capacitance of 34.26. The inverse of this, I'm sorry. That gives me 34.26 microfarad. Okay, so this one is for part B. So the amount of capacitance I need to introduce here is 34.26 microfarad. Okay, then the the last part to this whole thing is we want to calculate the new current source. Okay, the original because now it drops down, so S1 I can calculate from this triangle. So S1 is the new apparent power. So S1 is equals to square root of P square plus Q1 square, the new Q. So equals to square root 500 square plus the new Q. The new Q that we want is 296.68 square. So that gives me about 581.46 VA. So that's the new power compared to the original 1000. Okay, and the original current was, or okay, rather the the IS, the magnitude of the new current now is just power over V, the new power. So the new power now is 581.46 over 230. That's equals to 2.53 ampere. In the polar version is 2.53. At the angle, the new power factor now is 30.68, which we calculated earlier. So now we can compare the original current. The original current was 4.348 ampere. Now it has dropped to 2.53 ampere. Hence improving power factor will help reduce the current in the circuit, and this will help to reduce the energy loss in the cable, as we have discussed in the class. Okay, so thank you for watching example 4.3a. I hope you learned something from this video. Bye bye.